Big Bang predictions. When we think about the scientific method, at this point we have our hypothesis, which, based on the standard model, is that the universe began small and hot. So our next step in the scientific method is to test the hypothesis. And the way we test that hypothesis is by making predictions. And if our predictions come true, then that helps to confirm our hypothesis. Well, with our standard model, there are a number of predictions that do come true. Our first prediction is that it predicts the expansion of the universe. Now, one can argue that this is a somewhat circular case because it was the expansion of the universe that led to the development of the idea of the Big Bang. But the two are mutually consistent. The cosmic background radiation, CBR. We have seen two observations of the cosmic background radiation that have matched predictions. So we saw Penzias and Wilson observe the 3K background. And we had the Cosmic Background Explorer, which gave us the black body curve that exactly matched predictions. So these were two very powerful cases where the predictions were confirmed by observation. The abundance of light elements. So here we're talking primarily about hydrogen and helium, though there's some others in there as well. Lithium, beryllium are also in the mix. The early universe was hot enough for fusion. Which is going to produce everything in my list over here except for hydrogen. And based on the model, we can calculate how much of each is produced. So that calculation led to a prediction. Basically, they were predicting how much helium should we see, how much lithium, how much beryllium, how much hydrogen should we see. And their predictions are correct. We see the relative abundances of these four elements, plus their isotopes, which is what some of these variants are. So like 3 helium and 4 helium are isotopes. Those have same number of protons but different numbers of neutrons. Same thing for hydrogen and deuterium. Those are isotopes. So they were able to predict how much of each kind should have been produced early in this universe. And then look at the universe today and see how much of our universe is composed of each of these elements. And the numbers match. Neutrinos we have not talked about. This is a byproduct of fusion and some other events. Also, radioactive decay sometimes produces neutrinos. But the models said that there should be 3 of these things. These are basically high energy particles that are produced. And it wasn't until around the year 2000, I think it was a little bit before, the 3rd neutrino was discovered. So this had predicted 3 kinds of neutrinos long before the year 2000. So this was a discovery that took some time, but did in fact confirm the model. So we have lots of evidence that confirm our model, where the predictions come true. But the model is not perfect. There aren't predictions that don't come true, but there are things that we observe that the standard model doesn't predict. So here we're talking about the standard model. Universe began small and hot. So some of the things that it does not address. Why there's more matter than antimatter. In that early era, we had energy converted to matter. That's basically the reverse process of Einstein's E equals mc squared equation. But that predicts that every time you take energy and convert it into matter, you're going to get a particle plus its antiparticle, either an electron and a positron, proton, antiproton, neutron, antineutron. But if that's the case, then you would think we should see equal numbers of both, but we don't. As far as we can tell, based on what we observe, there's a lot more matter in our universe than antimatter. So what happened to the antimatter? We don't know. Our observations from WMAP showed these regions that were cooler. So the cool, dense regions are where stars and galaxies formed, which we wanted because we know stars and galaxies are here, and so there needed to be these places where they would form. But the standard model doesn't explain why you would have these small variations. We just know that those variations are there, but we don't have in the standard model any way of predicting this. Why the cosmic background radiation is uniform. Here we're talking about the fact that if this is us, so I'm going to use the symbol for Earth, we can look out in one direction, 13.7 billion light years, and we can look out in the other direction, 13.7 billion light years. And these 2 points that are 27.4 billion light years apart are the same temperature. Well, we know that in order for things to be the same temperature, they need to have time. Now, it's like setting out a hot cup of coffee, and if you don't touch it, given enough time, it's going to cool off to room temperature. Well, similarly, if you have a universe that is all the same temperature, that means that it's had to have been able to exchange information with all parts. But if your parts are farther apart than the age of the universe, then how have they come to the same temperature? And the standard model does not answer that question. Why is the density of the universe so close to critical density? When we look at the possible futures of our universe, and we had a graph of size versus time, and we looked at three possible futures. We have a closed universe, a flat universe, which is also critical density, or an open universe. Well, if you compare all three for present day, they're all very, very similar. So regardless of what the density of our universe is, it's close to critical density. We just don't know how close. Standard model, it could produce any kind of universe. It could have a very high density universe, which would just collapse instantly. Or it could have a very low density universe that would fly apart before stars and galaxies could form. So our universe is at just the right density for all of the stars and galaxies to form, for planets to form, for us to appear. There is nothing in the standard model that predicts this, because it could apply equally well to any kind of universe. It doesn't have to be a universe that has a critical density. So we have weaknesses in our model. It does a good job of predicting a lot of things, but it doesn't predict everything. And so, in terms of the scientific method, our next step is we are going to modify the standard model. And so the next two tutorials are going to deal with that idea.